Okay, good morning, everyone. I hope you had a good Easter long weekend and are ready to start winding down the term. So some of the announcements for today is there's only one more Prairie Learn homework, and that's due on the last day of classes. So that's Thursday of next week. If you're doing the hands-on bonus projects, then please send me your links to your videos by Monday. Because there was no class on Monday, and then we have tutorials scheduled on Monday. There are no tutorials this week. We will do our last tutorial in the last week of classes next week. And then the 121 labs are done. And finally, the last thing is that we're going to ask you to complete an end of term survey by Wednesday, April 10th. That's the last day of the Phys 121 classes. And so if you complete that survey, you will get 0.5 towards your final grade. If you ignore the survey and don't do it, then your maximum possible grade in the course would be 99.5. Every year, people, after final grades are calculated, some people will email me and say, hey, I got 79 in the class. Can you round it up to 80? And I'll say, no, sorry, I can't do that. But if you got, say, 79.2, and then you did the survey, that would take you to 79.7, which would round to 80. So this is potentially a way to get you above that threshold if that's something you're worried about. So let me show you. I've got here the link to the survey is in Canvas, and what I'm going to do is I'm going to share this. So here is the Canvas page, and let's see if I can find on here. So end of term survey. So here is the link to the end of term survey. All you have to do is click on that link, and it will open a survey which will start with some preamble, and then you have to enter your student number. You enter your student number just so that we can see who's done the survey and assign the 0.5 marks, okay? So if you don't enter your student number or you enter a fake student number, you're not going to get that credit. Okay, good. So then let's get back to this tablet. Okay, here we go. So we have two main topics left, and we have, including today's class, there's 4 classes left. So we're going to try to complete one of those topics today. That's going to be Ampere's law, and then we'll devote the rest of the class to the final topic, which will be kind of working towards Faraday's law, which was kind of the emphasis of the final lab number 8. So just before we get into all that, what we did last time is we imagined firing a charged particle through a region of space where there were uniform electric and magnetic fields, and those fields were perpendicular to one another. And what we found is that if we pass our particle through such a device, then only particles with a specific velocity will come through the other side undeflected. For that reason, this device is called a velocity selector, and the speed that makes it through this apparatus without being deflected is given by the ratio of E over V. So it's the ratio of the electric to the magnetic field strengths. We ended up incorporating this velocity selector into another device, a mass spectrometer, which we could use to determine the mass of particles. And so this is used in physics and chemistry research all the time. The other thing we talked about was, well, okay, if we know that a moving charge passing through a magnetic field experiences a force, then a current is just a collection of moving charges, and so it must also experience forces in a magnetic field, and indeed it does. The the force that a current would experience is given by this I times L cross B, where L is the length of the current or the wire, and its direction is given by the direction of the current in that wire. So in this case, we have a current going off to the left. So our L would be to the left. We have a magnetic field that's pointing out of the screen. And so I curl my fingers out to be out of the screen. My thumb gives the direction of the force. We would have an upwards force on the current that's drawn at the top of the screen there. And then we said, okay, that's kind of interesting. So a current experiences a force in a magnetic field, but I also know that currents create magnetic fields. So what we could do is we could have parallel currents, and we could imagine that, say, the top current creates a magnetic field at the position of the bottom current, and that bottom current will experience a force due to that magnetic field. And we worked this out and we said, oh, that's kind of interesting. If we have currents that are parallel to one another, then those currents attract. And they attract with a force equal to mu naught times the product of the currents times the length of the wires divided by 2 pi d, where d is the distance between the parallel currents. Of course, if we reverse the direction of one of those currents, then the two wires will repel one another rather than attract. But the force with which they repel one another would be exactly the same. It's just the direction that would reverse. Okay, so that's a little summary of the things we were working on last week before this extended weekend. So what I want to do today is I want to talk about Ampere's law. And this is going to be used. So it is used to find the magnetic field due to various configurations of currents. So if you think back kind of closer to the beginning of the term, we had something called what was it called? Gauss's law for electric fields. And this Ampere's law is going to be kind of the analog of Gauss's law for magnetic fields. So this is like the analog of Gauss's law, but for magnetic fields. Okay, what I'm going to do is I'm going to write down what the result is, and then we'll go through the process of trying to show that that must be the result. So we will find that Ampere's law is going to be given by, it's going to be an integral of B dot dl. Okay, so this little circle around the integration sign, we had that for Gauss's law as well. This means that we're going to integrate around a closed loop. And we'll see that in just a second. What that's going to have to be equal to is going to be constant mu naught times something that we're going to call I enclosed. Okay, and so this will be our Ampere's law. Okay, so in order to get this result, what we're going to do is we're going to start with going back and thinking about a long straight current. So let's first recall that the magnetic field due to a long straight current is given by, so the result was the magnitude of the magnetic field would be mu naught I divided by 2 pi r. We used this result for the last class when we were trying to figure out the force of attraction or repulsion between parallel and anti-parallel currents. So we made use of this result recently. Let me just draw a long straight current. I'll draw it maybe on a fresh page. And so here is going to be our long straight current. Maybe we have a current going out to the right. So what we know about currents is that they are sources of magnetic fields. If we want to get the direction, we put our thumb of our right hand in the direction of the current, and our fingers curl around in the orientation of the magnetic field. So in this case, we have a magnetic field pointing out of the screen above the current, and then below the current, they're pointing into the screen. And so we have these magnetic fields that are looping around. And it looks something like this. We have these magnetic field lines that are looping around like so. Trying to draw these symmetrically. Okay, and the R in this equation is the distance from the observation point to the current. And so if I want to know the magnetic field at this point here on this little field line, the distance that is relevant is this distance R. Okay, and so the strength of the field is just some constant times the current divided by R. Okay, good. So what we're going to do is we're going to try to evaluate that integral for a loop that goes around this wire. So let's try to evaluate the integral B dot dl for a loop that surrounds the current I. Okay, so we're going to have to pick a loop, and we're going to pick a loop that is circular in shape, and we're going to have the current pass through the center of the loop. So what we'll do is we'll pick a loop that we'll place it just beside this blue magnetic field line. And so this red loop is our integration path. And so we're going to choose the loop or the integration path such that it is always parallel to the magnetic field, such that it is always parallel to the magnetic field B. The reason we're going to do that is because we have a dot product to evaluate, this B dot dl, and I want that to be simple, right? In general, B dot dl is B times dl times the cosine of theta, and the theta could be any arbitrary angle if I pick some complicated path. But if I pick the path that I've shown here, the red one, then if B and dl are always in the same direction, then the angle between the two is always 0, and the cosine of 0 is always 1. And so it makes the dot product easy to evaluate. So around this loop, if I pick some little point, dl is constantly changing its direction, but it's always tangent to the integration path, which is parallel to the magnetic field. So if we do this, we could say in this case, B dot dl is just equal to B dl cosine of 0, but cosine of 0 is 1. And so we just get B times dl. Just like in Gauss's law, we're always looking for these symmetries where we're going to make evaluating the dot products and the integrals easy. And so for the dot products, It's choosing paths that are perpendicular or parallel to magnetic field lines. And then we want the magnetic field to be constant everywhere along our integration path, so that if it's constant, we can take it outside the integral. So let's next notice that the distance from the wire or the current to the integration path is always the same. And so it's always a distance r away from the wire, right? So we've drawn r on our little diagram there. And so everywhere, no matter where we are on that red path, we're always the same distance r to the current. And so since current is the source of magnetic field, if I'm always the same distance from that current, I would expect the magnetic field to always be the same everywhere on that path. Same in magnitude, but changing direction. So therefore, B has a constant magnitude along the red integration path. Okay, so what we're trying to evaluate is this B dot dl integrated around this red path. What we've said so far is, all right, the dot product just evaluates to B times dl because cosine of 0 is 1. B is constant for the path we've chosen, and so it can come outside the integral. And we have B times the integral of dl. But if our path is a circle of radius r, if we add up all the dl, all the steps around the path, what do we get? We get the circumference, which is just 2 pi times r. This is the circumference of our circular path. Okay, and so therefore, we end up with this B dot dl just evaluates to B times 2 pi times r. Okay, so we're almost where we need to be. The last step is to say, okay, we're considering a long straight wire. And for a long straight wire, I already know that the magnetic field is mu naught I divided by 2 pi r. So I know that this is mu naught I divided by 2 pi r for a long straight current. And so we have mu naught I divided by 2 pi r for the magnetic field times 2 pi r from the integration around that circular loop. And so, of course, the 2 pi r's cancel, and we get the desired result. B dot dl is equal to mu naught I. And this is Ampere's law. Usually, this current will label as the current inside, or the current that passes through this loop. So this is the current that passes through the integration path, which is sometimes called the Amperian loop. So for Gauss's law, we had these surfaces that we had to draw, and we called those Gaussian surfaces. Here for Ampere's law, we have integration paths, integration loops that we have to draw, and those are often called a Amperian loop. Okay, so usually the current is labeled as I enclosed. And so what we get, therefore, is B dot dl is equal to mu naught I enclosed. And this is Ampere's law. Now, what you might do is you might complain that, well, okay, that's a nice result, but we've only done this for a specific case of a nice circular path centered on a current passing through that loop. So the current passes through the center of this loop. So what I want to do is I want to consider what happens if we do the same calculation, but we deform the path. So does this result hold for some arbitrary path around a current? Okay, so the question is, what about an integration path of arbitrary shape? So does Ampere's law still hold? All right. So what I'm going to do is I'm going to choose another path. And so this time what we'll do is we'll have we'll take an end view of the current. So end view. And so what we'll do is we'll say, all right, here's my current I, and this current is coming out of the page. Okay. And so if the current's coming out of the page, I can put my thumb in the direction of the current, and my fingers tell me that the magnetic field is going around in the counterclockwise direction. All right, so we can draw some field lines that come around. They're circular and they're going in the counterclockwise direction. So here's the magnetic field. There's one that's close to the current, and here's a field line that's a little further away. Okay, so that's what the magnetic field's doing around this current. And we know that the strength of the magnetic field is mu naught I over 2 pi r. All right, so I'm going to choose an integration path. I'm not going to make it a circle, but I will make it some specific geometry, and we'll see why in just a second. All right, so what we'll first do is we'll follow a section along a circular arc, and I'm going to call this part 1 of my path. Okay, and then what we'll do is we'll follow a radial trajectory. And so this is going to be my radial trajectory in towards this inner field line that we've drawn. And this will be step 2 of my path. And then I'm going to follow another circular arc. And this is going to be step 3. Then we'll have another radial section. We'll jump back out to the larger radius, step 4. And so you can see what's going to happen. I got to close this path. So I'm going to come around here. We'll go a certain distance. Oh, I can clean that up a bit. We'll go a certain distance along this radial section. This will be step 5. Sorry, this is a circular arc. And then now we'll go back along this radial section. Step 6. Then we have, let's see, I've got to connect these now. So this will be step 7 on this arc. And then finally, we close our loop with step 8. All right. So you might even look at that and say, well, that's not arbitrary. You picked a certain geometry. But what I'm going to claim is that I could make any path I want out of infinitesimally small radial and circular arc sections. And so you can draw any smooth path you want around this loop. It could always be decomposed into radial and circular segments. You know, you can make them, you might have to make them really tiny to make that smooth shape, but it could always be done. Okay. All right. So we can form any path around the current I using small radial and circular arc segments. All right. So what we're going to try to do is we're going to try to show that B dot dl along this path is also equal to mu naught times I. And if we can do that, then it must be true for any path that goes around this current. So let's evaluate the integral of B dot dl. Well, the way we're going to do it is we're going to say, well, what we would first do is we would start our little journey around this red path, starting with the first segment, 1. And so we would, around path 1, we would do this B dot dl, and then we do this around path 2. And it would keep going until we got to part 7. And then finally, part 8. So we've broken up our integral into these 8 little steps. Okay, so let's consider one of the radial paths, or let's say radial sections. So the radial sections are all the even ones. So they're 2, 4, 6, and 8. All right. What is the direction of the magnetic field relative to the radial path, say number 2? They're perpendicular to one another, okay? So for these segments, we have that B is always perpendicular to the DL. So here, DL around my path is radially inwards, but my magnetic field are these circular arcs. So they're exactly perpendicular. And so therefore, what we're going to have is that B dot dl is going to be equal to 0 in this case. Because B dot dl is going to be B dl cos of theta. Theta is 90 degrees. Cos of 90 degrees is 0. So what we'll find is that all of these even segments are going to contribute nothing to our integral. So we have only the parts that follow these circular arcs that are remaining. Okay. So we're going to next consider the circular arc paths. These are the odd ones, 1, 3, 5, and 7. Okay. In these cases, B is parallel to DL, right? Because those circular arcs are just following exactly those magnetic field lines. And so that means B dot dl is just B dl. Just like before, for these sections, B will be constant. And B is constant in magnitude. along these sections. Okay, and so that means we're going to have something like, let's take path number 1. This is going to be B dot DL. It's going to be B DL. We get rid of the dot product. Magnetic field is constant. And so this is going to be B time, sorry, this needs to be a DL. Okay, so we need to go a bit further. Let's go back to our drawing and let's label a few things. I'm going to call this radius, I'll call this radius, say, R2, and I'm going to call this radius R1 here. Now, we're currently working on path number 1 here, and we need to do the integral of DL along path 1. So it's just the length of that arc. So if we go down here and we say, this is going to be the length of arc 1. How do you calculate the length of an arc? Who remembers? You have a circular section. You have a section of a circle. You want the length of that arc. It's the radius times what? It's the radius times the angle that arc spans. And so I'm going to label for section 1, the radius of that angle is theta 1. Or sorry, the angle that we pass through is theta 1. And so this is going to be R2 times theta 1 for that first path. Okay, so then what we have is that this, for the first path, this B dot DL is going to evaluate to B times R2 theta 1. This makes sense if we think back to the first problem we did where we had a circle around the loop. That arc length is the same thing. It's just that theta 1 for a full circle is just 2 pi radians. And so it would be 2 pi times R, which is the circumference of the circle. This time for our path, we don't have a full circle. We just have a section of it. Okay, fair enough. But for path 1, we know that B is equal to what? Well, it's mu naught I divided by 2 pi times the distance from the current, and we labeled that R2. So what we can do is we can take this expression for B and sub it in there, and we would get B dot DL is going to be mu naught I divided by 2 pi R2 times theta 1. And the radius ends up canceling out. And so all we end up getting is mu naught I divided by 2 pi times theta 1. We'll get the same kind of results for all of the other circular paths, except instead of theta 1, we'll just have to pick the correct angle. So in fact, I can label all those angles. When we do path 3, theta 3 will be this section. When we do 5, theta 5 will be this angle. When we do 7, we'll get this angle theta 7 here. And if you look at this picture, let's just make a mental note. What's going to happen if I end up with theta 1 plus theta 3 plus theta 5 plus theta 7? What's that going to equal? 2 pi, right? That'll go right around this circle. Okay, so we would say likewise, we would get the integral around path 3, which is the next circular arc, is going to be mu naught I over 2 pi theta 3. And we'll get the same for paths 5 and 7, where instead of theta 1 or theta 3, we would have theta 5 and theta 7. Okay, so therefore, the full B dot dl integral is going to be the integral around all the contributions from all these little sections. And we know that all of the even numbered sections, the radial parts, are all going to contribute nothing. And all the circular arcs are going to contribute mu naught I divided by 2 pi times theta. And so what we'll end up with is mu naught I divided by 2 pi theta 1 plus 0 plus mu naught I over 2 pi theta 2 plus 0 for the third path, mu naught I, 0 for the fourth path. Here's theta 5, there's no theta 2. The circular arcs are all the odd numbered. Then for 6, we would get 0, mu naught I over 2 pi theta 7. And then for the 8th path, we would get 0 again. Okay, this all simplifies to mu naught I divided by 2 pi theta 1 plus theta 3 plus theta 5 plus theta 7. All those angles add up to exactly 2 pi, and we could cancel the 2 pi in the denominator. And so therefore, we get our desired results. The integral of B dot dl is mu naught times I, and this is going to be the current that's enclosed by the loop, I enclosed. So we've recovered Ampere's law for an arbitrary path. Okay, good. So what I want to do, and maybe we'll save this for Friday, is I want to apply this to the solenoid that you used in lab 7 to measure Earth's magnetic field. Well, in fact, why don't we try to do it now? Let's apply Ampere's law to a solenoid. Okay, so let me remind you of our solenoid. The way you could make it is just take a cylinder of plastic or something like that. Any kind of cylinder, the cardboard tube that you get from your saran wrap when it's empty. And then you're going to take a wire and you're going to wrap it around the tube like so. And then it'll come out like this. And so we'll put a current on this coil of wire, and we'll call that current I. All right, so what we know from experience and lab 7 is that the magnetic field is not zero, and it's perpendicular to the axis of the solenoid, or sorry, it's parallel to the axis of the solenoid inside this cylinder. So from lab number 7, we know that B is not equal to 0 inside the solenoid, and it is parallel to the solenoid axis. So if I draw the solenoid axis here, something like that, then we're going to have a magnetic field inside. Let's see, if I put my thumb in the direction of the current, which is downwards in front of the solenoid. My fingers curl around so that the magnetic field is pointing to the right inside the solenoid. Okay, so we're going to have a magnetic field inside the solenoid that's pointing to the right. So here's our magnetic field. Okay, the other thing we know is that B is equal to 0 outside the solenoid. Okay, so out here we have B is equal to 0. Whoops, I'm gonna move that over just a bit. Oh, why didn't you do that? Okay, good. Okay, so what I want to do now is I want to apply Ampere's law. And to apply Ampere's law, we have to pick a path to integrate around. So to apply Ampere's law, we have to select an integration path. And the criteria that we're going to follow to choose our path is I want along every part of my path, I want the magnetic field to either be perpendicular or parallel to the path that I draw. So want B to be perpendicular or parallel to every segment of our integration path. Okay, so I'm going to choose a path. The first thing I'm going to do is I'm going to say, okay, inside the solenoid, the magnetic field is along the axis. And so what I'll do is I'll choose my integration path to be parallel to that field inside the solenoid. And I have to have a closed path, so it has to loop back on itself. And if the magnetic field is to the right, so to the right, then what has to happen is if I choose part of my path to be directly down or directly up, I can be perpendicular to the magnetic field. So I'll call this first part section 1, and then I'm going to take a path down, which is going to be section 2. Outside, the magnetic field is 0. And so I don't care what my path does outside of the solenoid. It could be some complicated shape. I don't really care. Here's path 3. And then I need to go back into the solenoid to close the loop. And I'm going to make step 4 be perpendicular to the magnetic field once we get inside to the solenoid. So, and I'm going to choose the purple path. Okay, and so what we can say is 1, or let's say segment 1 is parallel to B. Segment 2 is perpendicular to B, or B is equal to 0. So B is equal to 0 once we get outside the solenoid. It is going to be perpendicular when we're inside the solenoid. So let's just make that. So this is inside, or B is equal to 0 outside. And the same thing for 4. 4 is perpendicular to B when we're inside the solenoid, or B is equal to 0 when we're outside. And then for 3, B is equal to 0 everywhere. Okay, so that's what we know about the path that we've chosen. And so all we have to do now is to evaluate this integral, and I think we have just the right amount of time to do that. So Ampere's law is this B dot dl. We're going to do the same thing like we did in a previous example. We're going to break this up into 4 parts. So there's the first part, which is part 1. And then we have part 2. And then 3. And then 4. Okay. Now, some of these are really easy to deal with. For example, in section 3, B is 0 everywhere. So this thing's just going to vanish since B is equal to 0. All right. Then we've got 2 and 4. So when we're inside the solenoid for 2 and 4, B dot dl is 0 because the path and the magnetic field are perpendicular. Parts of 3 and 4 come outside of our solenoid, they come below, but when we're below, the magnetic field is equal to 0. And so no matter where we are on those 2 paths, we're going to get 0 for these 2. And this is because B is perpendicular to DL or B is equal to 0. So B is perpendicular to DL when we're inside the solenoid, and B is equal to 0 when we're outside. And so all of this just boils down to dealing with only the first path. And for the first path, B and DL are parallel, so the dot product goes away. And then when I look at this, along the path 1, I'm always the same distance from all of the coils of the wire. And so there's no reason to think that the magnetic field would be changing. So along path 1, we expect B to be constant. And so we get B times dl times the integral of dl. And so now what we have to do is we have to assign a length to our segment of this path. And let's assign this length to be L. Okay, so if we take a bunch of steps along path 1, the total length of those steps that we take is just L. L. And so we end up with B dot dl is equal to B times L. Pretty simple. And by Ampere's law, that has to be mu naught I enclosed. So the last step to finish this problem off in the 2 minutes that we have is to find out how much current passes through our little loop. And so let's go back to the figure. If I have current I going through this loop coil, how much total current passes through the purple loop as I've drawn it there? How many times does the loop of wire pass through the purple path? Twice, right? And so in general, if I have a tightly wound coil, the loop will pass through this purple path n times. The way I've drawn it, n equals 2. But in general, you'd have tightly wound coils, and you could have many, many times this wire is passing through this loop. So in general, the blue wire or current passes through our purple Amperian loop n times. And so therefore, I enclosed is equal to n times I, because each time the wire passes through, we have an amount of current I that goes through our integration path. And so therefore, what we end up with is B times L is equal to mu naught N times I, or B is equal to mu naught N over L times I, and this is the magnetic field due to a solenoid. And this is exactly the results that you were given and made use of in lab number 7. Okay, perfect. So that's where I'm going to stop. What we'll do is we'll review this result at the start of next class, and then we'll start beginning our last topic of Physics 121, which happens to be the most interesting topic, and it is Faraday's law. It is generating electrical power from mechanical motion. Okay, thank you very much.
Can I ask you a question?
Yeah.
For the proof, you did it with just loops, circle loops, right?
Yeah.
With the 2 pi r.
Yeah.
But how does it translate to